Hello, everyone. Thank you. Wait, just one. Welcome to the webcast, Mastering Python's Async Features with the new Async and Await keywords. I'm Michael Kennedy. Some of you know me, some of you don't, but I started Talk Python training and run some of the Python podcasts. You can follow me on Twitter where I'm at mkennedy. And I'm really looking forward to talking about this topic. I feel like it's definitely an underappreciated and underused aspect of Python. So I'm looking forward to that. Before we get to it, though, let me tell you really quickly about Wintellect. They do all sorts of good stuff. They do consulting. They build custom software. They're really big in the instructor-led in-person training business, so check them out for that. And they also do on-demand through their Wintellect Now. They've written a lot of books, many of them very well respected. And they also now offer mock courses, Microsoft official curriculum. So if you're interested in that, check that out. Contact my friend Martha Guerin at mguerin@wintellect.com. I'll put that email address up at the end. For now, let's talk about Python. At the beginning of these, one of the first questions is, all that code that you're typing, do I get that? Yes, you'll get that. So if you go to the repo, github.com/wintellect/wintellect webinars, I'll be uploading everything you see me type, everything we're starting from, and the final result. You'll find it there. So you'll be able to take this with you. Also, we're recording this. Some folks couldn't attend, got those questions as well. So if you want to go back through it, or a colleague or somebody who should have seen it but didn't, you can share the recording with them. Okay, some bizarre little artifact on my screen there, but let's talk about asynchronous programming. So if we look at the definition of what is asynchronous programming, you'll see that it's, in computer programming at least, refers to the occurrence of events independent of the main program flow and ways to deal with those events. And hold on, let me restart that. That looks really not very legible. There we go. These events may be outside, such as arrival of a signal, something landing in the queue, request to a web server, something like that, or they could be started by the program. Like maybe the program needs to send a welcome, glad you registered to my site email, and it doesn't want to wait to say, your account's created and all that, right? It's going to do that in the background. So why did I show you this? Well, there's a couple of things that are absent from this definition, and that's going to be important for really understanding how async and await work. What you do not see here is asynchronous programming is when you start a bunch of sub-processes to do multiprocessing. It's also not, hey, I'm going to create a bunch of threads, and the main thread does something and the background thread does something else. Like, it's not talking about those things. It's just talking about things happening alongside of each other, and that's going to be important. Now, when we look at why people care about asynchronous programming, why do you want to adopt this for your code? There's two major drivers. So especially in Python, it's important to understand what your goal is, because the tools and techniques that you can use apply to one or the other. It's not really even, right? So some techniques are much better for performance, some are better for latency, things like this. So the first one would be for speed. Check out this graph. So if you think back to Moore's Law has been around for a long time. That's the top reddish maroon color line here. We often have thought about Moore's Law as how fast your computer goes. And in the early days, if you look at the green line, or a little bit later once they started measuring it, the blue line, single-threaded performance, those lines tracked pretty well. Moore's Law and performance were pretty similar. And then something happened, and this something happened around 2005, and the performance in terms of speed and computational power kind of flattened out. But Moore's Law kept on going. That really talked about transistors, and those kept going, but the individual CPU cores didn't get much faster. Sometimes they even slowed down. And what happened was we got more and more cores. So let's look at a real simple example here. This is a screenshot from this computer. It's my MacBook Pro. It's a Core i9 with 6 cores, but they're hyper-threaded, so it looks like 12 to the operating system. And I wrote this little bit of Python code here. I opened Python. I said, while true, do something, right? Basically, hammer the CPU as hard as you can, but only on one thread. And look at the amount of performance I'm getting from this computer, 9.5%. And this is the entire operating system, not just my program. My program's like 8.3 or something. 1/12. So if we only write single-threaded code, we can't take advantage of modern hardware, right? To say, well, my program can only use 8% of the computing resources available to it, and it's going to get worse in the future. That's not a great option. Okay, so single-threaded performance or single-core performance, while okay, is not really what we want to aim for. Let's talk really quickly about some expectations, I guess, when you're thinking about this concurrency stuff. We have a program here, and it has parts of it that have to be done single-threaded. One thing has to happen after the other. Just algorithmically, it can't be split apart, okay? That I've colored yellowy orange, and some parts can take advantage of multi-threading. So maybe these parts, we could rewrite the algorithm, we could use new techniques, we could use async and await, and we could get better performance, right? Now, if you think about this programming, think about the complexity of converting that green bits to some form of concurrent operation. If we could have 1,000,000 CPUs, we have 12, if we could have 1,000,000, we could make those go to 0, right? So how much better could this program possibly be if we added concurrency in this fanciful world of like we run it on the cloud, completely distributed, whatever? Well, if that's 15 and that's 5, the very best you could do is 20%. So when you start thinking about concurrency and performance, you got to think, is it worth applying this added complexity to this? Like, how much of an improvement can you get? We'll see a lot of times it's mostly green. So it's really, truly a big boost. But in this case, not too much. One of the times it is green is when you're waiting. And this is going to be the focus of most of this webcast, is dealing with when your program is not technically idle, but it's just waiting on an external system of some sort. Maybe it's trying to write to disk and you're waiting on the disk. Maybe it's trying to talk to the database and the database is running the query and it's going to get back to you. You're talking to an external service like Stripe or something else, right? A microservice maybe. There's a lot of times when we could use asynchronous behaviors while we're waiting. And that's really what async and await are all about. Okay, so let's think of a web server in this world where we're talking about calling other systems. So this first one is going to be the synchronous version, and we'll see maybe how we could apply async, and then we're going to write some code, okay? So in this one, a request comes in, and the green bar where it has the name of the request, that's actually how long in terms of time it takes to process one. Maybe while it's partway through request 1, we get 2 and 3, and those don't, the 3 doesn't take very long, but it's at the back of the queue, so it's got to wait. If you look at how long do these actually take to respond, well, 1 comes in, 1 goes out, no problem. But 2, well, it's backed up for a long time, and 3, even though it's tiny, it's like 5 or 6 times longer wait because it's waiting. Okay, it's waiting for the other stuff. But if we dig down inside one of these, you'll see that most of the time, what our web app is doing is waiting on other things. Maybe this is a microservice that it's calling over to. In this case, I've highlighted as a database, and these parts, our program just stops. We're just waiting on that database. What if we could do stuff while that was happening? Okay, so if we rewrite this code so we can actually break it up and do work during those waiting periods, we can still process request 1, but partway through, we're just waiting. So if we request 2 comes in, no problem. We're waiting on the database for 1, so we can just grab it and answer it. Similarly, when request 3 comes in, you can see much, much better. This is way more what you'd like to see. All right, and again, if we zoomed in, that's because these parts that used to be red, now we can do extra work during these periods. And that's what async and await are going to let us do. It's going to let us write really simple code that just says, during these green parts, if you got something else to do, go do it. Otherwise, I'm just going to hang out here. All right. Okay. Now, in Python, we have a bunch of different ways to write asynchronous or concurrent code. And conceptually, let's break those into 2 things. One where we could do more at once, and others where we could do things faster. Do more at once is the scalability latency thing. Do things faster as I'm trying to break an algorithm up and run it on all the cores. So over here we have Async IO, that's async and await, and we have threads that let us do more at once. And over here we have multiprocessing, and we actually could write stuff in C or Python, and that lets us do things faster. We also have some libraries like Trio and unsink that make it easier to do these types of things. If we have time, we'll talk about unsink at the end. So In some programming languages, you might put threads in both of these areas, right? You might put threads and they do things faster as well. But in Python, we have this thing called the GIL, the Global Interpreter Lock. And this is an interesting thing. It really is about managing the memory associated with Python objects as instructions are executed. But the net effect is that Python will only run one Python instruction at any given moment ever per process. So that means that we can't really use threads for computational stuff. It turns out to not be that big of a deal. We have other ways to deal with it. But if you want to learn more about it, check out realpython.com/python-gil. Okay, so if we think of a typical concurrent program, like conceptually, you say, okay, well, I'm gonna have this main thread, and I have some background threads. And if I got to do extra work, I'll kick off the background threads. Maybe we'll do a fork join pattern and wait for them to be finished. We'll get the result and we'll keep on going. That's fine for threads and multiprocessing and all that kind of stuff. But when you think about async IO, you have to think differently. Go back to that original definition I got from Wikipedia, right? So if we're doing IO-driven concurrency, it's about trying to take the time that we're waiting and allowing our program to do other stuff until we're done waiting. So if we have a single thread here, we could actually break up different tasks, different things we want to do, different web requests or web scraping jobs or whatever, and break them into the parts where we're not waiting. Like the first one might be those parts. The next one might be those parts, and so on. And if these are small relative to how much we wait, like 1 second to process, 1 millisecond to process the database response over 100 milliseconds to get it, then interweaving these things makes it feel like it's effectively running in parallel all at the same time, even though it's actually not. So this thing right here, this is the async event loop. And we'll see how we use async and await to do this little breaking up of our tasks. Okay, now, before we move on to this, I want to ask a couple of quick questions. So I'm going to show a couple of polls just to see where you all are coming from. And I know, let's go and launch the poll here. And you all answer this. I'll give you just a second. All right, about half of you all are doing Python, which is great, and about 30% C#, and then some other. Okay, great. Now, that's good to know. And then let's also talk real quickly about how much experience you have with async and await. All right, super. So 12% none, 45% know that they exist, 38% have used them a couple times, and 5% of you are experts. All right, super. So let's go over here and work with some code. So I talked about having the code for all of this. So this is the Wintelect repo that I forked. I'll upload this in a little bit. So we're going to open this in PyCharm, and I want to go over here and create a virtual environment. I have a little shortcut. You can see the command at the top. It's just creating a virtual environment and activating it and making sure it's not using an outdated pip, which is always frustrating to me. And then I'm going to open this here in PyCharm. Okay, let's just make sure, that it's using the right interpreter. It sometimes guesses right, sometimes not. There we go. Okay, so we're going to look at a couple of different projects here. We're going to start out looking at something that seems like maybe it doesn't have anything to do with multi-threading, but is actually really an important building block conceptually. Then we're going to look at this concept of a producer-consumer, and then we're going to do some web scraping, and then we're going to do a mixed mode parallelism, if we have time, with this thing called unsink. So let's start out with this simple generator here. Now we'll go ahead and run this. And all it is the Fibonacci series, okay? But it computes it in, let's say, a less optimal way. What it does is it says, you give me the number of Fibonacci elements that you want, numbers of numbers in the sequence, and it will generate that as a list and give it back. But remember, the Fibonacci series is computed by going, let's take these two numbers, add them, take the next two numbers and add them, take the next two numbers, add them, and so on to infinity, okay? Not up to 200 or something, to infinity. So what would happen if we took this away and said there's no limit, and we just said, you know, just do this forever. Let me make a duplicate so you have both in your example here. All right, what if we take this away? And that would be just an iterable. We say, you know what, we're gonna go compute all the numbers. Well, PyCharm says, you know, that's never really gonna be reached. And of course, we're gonna run either out of time or out of memory, depending on which one we're willing to wait less on or have less of. But it's definitely not gonna turn out okay. But we could rewrite this as a generator, right? And instead of appending the item, we could just say, here's one of the items and compute it on demand, okay? And now if we run this again, super fast, we get the same thing. But here's the idea, like this, the way this worked before was it would do all of the work and then we could process the work, right? But if we set a little breakpoint here, maybe one here as well, and we debug into this, we can step over this. And what we get back is not a list, we get a generator. And when we iterate the generator, I'll step in. Now we're over here processing the first item. Notice 1 and 1 for the items. When we step in, now we're here, we're printing it out. Go back to the list. And now we've only done one step of this infinite sequence. We haven't computed all the numbers, we computed one of them. If we go through the loop a second time, now we've computed the second one, you can see next is 2. Now we've done a little bit of work. Step it again, we've done a little bit more. So this ability to use these coroutines and these generators to say, I'm gonna do a little bit of work, and then I'm gonna go do something else, and I'll come back and resume the work. Conceptually, that's really similar to what happens when we're working with async and await. We might start an operation, let some of the operation return, do some more work, and then kind of resume it just like we are this generator, okay? So conceptually, the idea of generators and the ideas of multi-threading and async and await are kind of the same. They're not internally the same, but similar. Okay, so let's go look at this other item here. Now notice I have 2 subfolders for each of these. I have a produce sync and a produce async. And that's because I want to give you the starter code so you can take it the way it was and then adapt it to what we're doing here. Now, this one that says async program is actually just a annotated, commented up copy of this non-asynchronous version, the synchronous version. So right now it's the synchronous version, but we're gonna adapt it. Now notice we're using a cool package here called Colorama, and it's in the requirements there. Okay, so I'm gonna just pip install that real quick. Program won't run without that, but I find when we're doing multi-threaded examples, it's super helpful to have color to say this part of the programming is doing this, that part's doing that, and you can see them interweave, and you know color means this part, that part. So let's just talk through what this thing is real quick. Okay. So the idea is, you know, maybe you're working with like a queue of data. So this could be something like literally a queue data structure, or it could be something like Redis, a Redis queue, but something is putting work into the system and some other part is picking up that work. And at the moment, we're doing this all in the same process. So we got to deal with this concurrency thing. So here's the idea. We're going to have a shared data structure, which is a list. We're going to have 2 operations that are generating data. If we look at what that is, you can see it's super simple. It just creates like kind of a message or a piece of data in the time that it happened. Let me make this a little more obvious here. This is the one thing going in this list. So if we make that a variable, call it message or something, right? The message is going to be this tuple. We're going to put that in the list, okay? Now to simulate this taking a while, we're going to say time.sleep. really, you can imagine this as computational work, talking to an external service, talking to a database, doing, I don't know, NumPy operations. Who knows? It takes some time, all right? And in particular, it's taking time based on an external system that has some kind of I/O, like a database or service. So we're going to do a couple of those, and then we're going to process the data. And process means go through, pull out the items, and if there's one available to be processed, we're going to go and work with it, and then we'll remove it from the list by popping it, and then we'll just print out some items, and then pretend that it took a while to work on it, okay? Great, now this is really contrived, right? It has sleep all over the place. We're gonna do one that doesn't have sleep, but I wanna start with a real simple example that doesn't depend on anything. All right, well, let's just run this and see what happens. So we run this async thing. Now, if we go back up here while it's running, you can see, it's not surprising, we're generating the item, so we're waiting on that. Oh, great, done. So that one finished. Now we're waiting on this one. Going through, working on it, and in a second, we're gonna go, now all the data is generated, we're gonna process it. But remember, most of these operations are waiting on something, simulated by time.sleep, but waiting on an external system. So it's going through, it's processing it. You can see it gets all the data, but it takes about 10 seconds of latency, right? From the time the item went into the queue till the time it was processed, the best we got was 10 seconds. Up here we got 20 seconds. It's really suboptimal, right? There's a lot of latency in the system. So how can we make this better with async and await keywords? All right, well, let's get started. So what we're going to do is we're going to convert these operations to run asynchronously, and we're going to convert this to some data structure that's a little more friendly. So you can see we're going to use a queue because right now we can ask the list questions like, list, do you have an item in you and whatnot, but we can't put our thread or our method, our coroutine to sleep until an item appears and then immediately wake it up easily with that. So we're going to use Async IO, and we're going to change this to an async IO.queue. The important thing is that the queue has a get and a put, and these are, if we look at them, go to definition, asynchronous. So they'll allow us to participate in this async event loop, okay? So that's easy enough. And then we're gonna change, I have down here that this is a list. This is gonna be an async IO queue, so we get nice autocomplete. Okay, now notice, this is a problem. We'll come back to that in a second. The other thing to do is we're gonna have to have an event loop. And let's go ahead and make that at the top here. It's gonna be an async IO.get event loop. And then down here, we can go and convert these into tasks. So we can say task 1 equals loop.create task of this. We have another one of those, and then the process data. Now notice it's not happy. It says we're expecting some kind of await thing or a generator or something, but none is probably not going to do it, or list or whatever that's doing. But we're going to fix that in just a second. And then we're going to have the final task or whatever equal to loop, I think it's just async IO dot gather task 1, task 2, task 3. And the last thing we'll have to do is say loop dot run until complete. Task 3, or final task rather. Okay, so what we're doing is we're saying start these running, all of them, and when one of them goes to sleep, when it awaits things, start pulling, just like a generator, from the other of them, okay? So that part's done, but notice there are some problems up here. It says these are supposed to be async. So let's rewrite these two. That really turns out to be super easy. Now, there's no append on the queue. That's a list thing. So instead, we want to do put, okay? Now PyCharm should give us a warning on line 33, but for some reason it's not detecting it. That's fine. Now to make our simulation async IO friendly, we have to change this from time.sleep to async IO sleep. It does the same thing, but it can be awaited. If we look at this again, it's an asynchronous operation. Okay, now that one is looking better. This one we want to do get. We don't have a number there. Now, instead of checking to see if it's there and sleeping, we can we're only going to get this item if it's available. Okay. Now, there's a problem here. It says this generator we got is not the right thing. So in order to actually get the value, what we need to do is break, kind of with the yield, like we did with the yield, we need to break up this method into the segments, right? These are the colored blocks in that async IO visualization I gave you all. So how do we do that? We say we want to wait until the result is available. So what we got here is a generator. If we await the generator, we get, when it's ready, the value out of it, okay? Now, we can only do this if we have an async method. Okay, so this is all good, except for this should be async IO sleep as well. And again, this is an async operation, so we have to await the result. The result is just time has passed, but there it is. So super simple. We've used a different data structure that we could await to put our thread or our processing to sleep. Then we use this one here, and in order to use that keyword in a method, you have to use the keyword there. Let's go fix this over here as well. This is an async method. Now we get the warnings I told you should have been there, that we're calling this function without await. It says put is not awaited. That's easy. And sleep is not awaited. Okay, I think we've converted our synchronous program to an asynchronous one. Let me just scroll through real quick, make sure I don't have an old time sleep or something bad. All right, we don't need time anymore. That's a good sign. All right, let's run it again and see what we get now. Look at that, all the work happening in parallel. The two generators are generating sometimes while these others should be waiting. The consumer got right in there and started working the items. So check this out. It happened, instead of in 30 seconds, it happened in 10. That's pretty good, but you can only process the items so fast. We had one consumer sort of thing. But check out the latency. Remember what we had before? It was 15 seconds, 12 seconds, 10.5 seconds. Now we're talking 0.28, 0.15, right? Much, much, much faster. So it turns out that this is about 60 times better in terms of latency, and that could make it better if we added more producers or more things that consumed it. So if we did, let's do it like this. We had maybe the same capacity. This was visible to you. Look at the latency now, 0. All right, soon as something comes in there, it's working, it's grabbing it, it's going, because we can consume the items faster than we generate them. I'm not going to leave it that way. It's not quite as interesting, but you can see that this latency can basically be made go away, because what is our app doing? It's just waiting almost all the time. So that's pretty sweet. Put that over there. Okay, so here's the starter, right? Here's how we took a regular program and we turned it into a concurrent version. Let's go back to the slides for just a sec. So what's the anatomy of an async method? Pretty straightforward. We're going to, of course, add the async keyword right at the beginning. You can't use await without some runtime error if you don't have async. We're going to await all the method call. That's how we get the item, the value out of the response. And of course, wait for it to actually give us a response. And we also maybe want to use some kind of data structure that is async IO friendly. Like here, we're using a queue, not a list. We saw the performance of the synchronous version was kind of crummy. It took 30 seconds, but the average latency was 15 seconds. Like, that's terrible. With just one consumer that was async, we saw that go down get much smaller. And of course, the average latency dropped to like a quarter of a second, and we can add more processing to get that really. Okay, so much, much improved. Now, one thing to talk about, we're still talking foundational stuff here with async IO and async and await and so on, is what we did was pretty coarse grained. And by coarse grained, I mean the amount of actual computation we did versus the amount of waiting was really small. We did a little tiny work to like print out something, and then we waited for half a second. It could be we're calling database calls, and the database takes half a second to get back to us because it sucks and we forgot to put indexes or something. But whatever, it's a slow database. We got to wait for it, right? And then we get the response back, and it's like 1 millisecond to process it. That's coarse grained. Well, if we're doing something much, much more frequently, a whole bunch more quick little pieces, you might consider using this thing called UVLOOP. So if, let's say, we're only waiting for 1 millisecond here, 1 millisecond there, and we're breaking it into a bunch of little tiny things to interweave operations, the actual overhead of the async and await and the async IO event loop, all of that stuff could actually start to make a meaningful difference. So this UVLOOP thing, it's about 3 to 4 times faster in that mode. It's built in C based on libuv and so on. So you can really easily swap this in and get better performance in the fine grain mode. In the coarse grain, it doesn't matter. You won't see any difference. So if you want to do that, you pip install UVLOOP, then you can import it. You set the event loop policy to UVLOOP, and then you just continue on as normal. Right? Nothing. That literally those 2 lines at program startup is all you need. Maybe it's helpful, maybe not. Be aware, last time I checked, UVLOOP didn't work on Windows, so that's a bit of a drawback, right? But it works well on Linux and Mac, and maybe you need it, but it's an option, something to consider, okay? So I can hear you saying, all right, that was cool that you made it much faster, that producer consumer thing, but that's not real. That's like you had time.sleep everywhere. Like, that's silly. It doesn't mean anything to me, Michael. How about you show me something real? Okay, so we're going to do another example where we go out and we do web scraping. And the thing we're waiting on is the internet, the cloud. Specifically, we're waiting on a web server and like the ping time and all that stuff on the network. We'll see that we get exactly the same or maybe even better type of improvements using async and await, and it's super easy. There's a great example of some guy sent me a message. We were talking, listened to the podcast, and we talked about using Async IO for web scraping and so on. And he had some project that took, I don't know, like an hour, a couple hours or something to scrape a whole bunch of sites. And he switched it to what I'm about to show you. And what happened was his computer started crashing. And the reason it was crashing was it was getting so much data back so quickly that it literally couldn't process it and ran out of memory or something like this. So this is pretty powerful stuff, and it's pretty straightforward. Let's carry on. So, like I said, this is a bit of a toy thing, but that's okay because we're going to do something better over here on web scraping. Same thing as before. We have an async and then we have a synchronous version. This one, the asynchronous version, starts out as the synchronous one, and we're going to convert it just like before. So let me copy this path. Let's do a little bit of pip install here. I'm going to do that one. And get that one. I'll show you what those are in a minute. We use Jarl, of course, and cjardet, and so on. So basically, what we have in the synchronous version is we have requests, colorama, again, and beautiful soup. We're going to go and do web scraping. Those are a nice pair right there. Over here, we're going to switch to this thing called AIO HTTP. So this is like requests, but it's built specifically to talk, to interact with the network in an async IO friendly way. Okay, let's go over here and do this. So where is the start of our program? Here's the main. So what we're going to do in our main is we're going to create an event loop. Actually, I'm going to create it right at the top up here because it has to be shared in some versions of Python. So here we'll have async IO, which we can import at the top and say get event loop. So that's cool. And then down here, we're going to convert get title range to an async method. async, if I can spell, would be way better. And then I'll say loop.run until complete and just give it this. All right, so we don't need these tasks because we're not trying to bunch them up. We can just do one here. Okay, so this is going to run that part, and that's cool. And we need this to be async because what we're doing here is we're first going to get the HTML and then we're getting the title. All right, let's look at get HTML here. Actually, before I do this, let me do it. Sorry, I want to show you. It's just going to be easier to just run it. I want to show you what it looks like when we run it. Let's keep talking through it, and I'll run it. So if we come over here and we call get HTML, it's standard request. What we're going to do is we're going to go suck a bunch of stuff off my website, so I'm not abusing someone else's server. I'll abuse my own. Use requests synchronously, get the response, make sure that it's a 200, 201, not like a 404 or something, and then get the text back by reading the stream off the network and sending it back. And we're printing that out in yellow. Then we take that HTML we got and we feed it down here to Beautiful Soup, and it gets the title. And then once it gets the title, we print that out here. All right, so let's see how this runs. So it's getting the HTML for episode 180, then 181, 182. You can see it's just waiting. What do you think this program is doing most of the time? I can tell you it's probably, well, let's not even tell. Let's do this. Let's say profile it. Let's see what it's doing. We'll run the profiler and we'll just ask, right? You can guess. It probably has to do with get HTML. Let's just see how much of its time is being spent waiting on the network. Wait for it, almost there. Okay, we go to the call graph and we zoom in. And we zoom in. And we scroll. Check this out. I go to the bottom. Okay. Our program is calling main. Main is calling get title range. We're calling get HTML 15 times. That's 96% of the CPU time is that. And that is just requests. Request.get. Right. It's just waiting and waiting and waiting. So here you can see that that is the end of sort of what our code is doing, right? We call that function and then it disappears magically into the request package and we wait. 97% of the time is waiting. This is such a good opportunity to make this faster using something like Async IO, because when you're waiting, if you use Async IO, it could just do other requests. All right. So with that now, obvious what's happening, we'll come down here and we'll upgrade these bits here. So this function, we want to be able to await these things. In order to do that, remember this has to be async enabled. Now here's our URL, but this does not support async. So I'm going to comment that out. And we have to write something. This might be a little bit funky for you. I know that most of you are Python developers. Some of you are .NET. We're going to write a with statement, with item, for you .NET people. That's like using some item, okay? All right, so what we're going to do is we're going to say with AIO HTTP, which is a third-party package. So we're going to import it as part of the requirements. Client session as session. Now, you might often write this, but it turns out that this is basically doing some network operations, and there's an opportunity to do other work while it's happening. So there's a syntax in Python that you have an async with block. That basically means do a with block, but take the result of awaiting that and drop it there, okay? And then we're going to do again async with session.get URL as response. And then here we have this text, right? So first thing we did is we made sure there was no error. So we said response.raise for status. That doesn't show up in autocomplete for AIO HTTP. Don't know why, it just doesn't. It's okay. Now this has got a response like header style, but maybe it's a big file, maybe it's streaming back. So we can't just get the text here. Notice it'll say you got a coroutine when you expected a string. So we have to await the string here. Okay. I think it might be text. Hold on a sec. Oh yeah, this is it's a little bit inconsistent, but there you go. It's a function. Okay, so we have that. We changed those 2 lines to these 4 lines, but you will see it's worth it. Okay, so this is good. Now there's no opportunity for async processing. This is just happening in memory, so it is what it is. All right, I'm gonna have to run our loop properly. And we need to define this to be async. And once it's async, we're going to have to await. Notice this is saying we got a coroutine expected to stir. That's because we have to wait to get the answer. Now, you're going to think, maybe you're thinking, oh, that's it. It's going to be amazing. It turns out not so much. Let me run it and I'll show you why. In fact, let me run it in a separate console here. Be a little better. So if we run it, you can see it's getting episode 180. It looks exactly the same. If we had other stuff happening, then it would be great. We could actually do more concurrency. But why is this not better? Right? This is a really important example because it feels like we made it async and it feels like it should be better, but it's literally the same in terms of performance, maybe even worse because now we're making it more complicated. The thing is, what we want to do is we want to go get all of the URLs for episodes 180 to 195. But what we're doing in code is we're saying, let's go give me the first 180, and then we're going to just not do anything until we get that answer. Then we'll process it. Then we're going to do it for 181, and we're just going to wait, not do anything. Like our program could do other stuff, but it's not really the way written. It's not taking advantage. Okay, so let's go over here and make a duplicate of that, and I'll leave the original there. Okay. So what we got to do is we actually have to go over here and start all of these things, and then we have to await them. Okay. So I'm going to do something like this. How am I going to do this? So we'll say something like this. For n in our range, we want to call get HTML with n, but that doesn't actually start the work. So we have to say loop.create task to actually say kick it off. Okay. So this list comprehension will say go start all the web requests. And then what we can do is we can loop through them. So we can do this differently, say for t in tasks, and we can await t. Let's put something different here. Let's say n comma, because you saw that we need the n here. So let's say n comma t, like that. Okay, so we'll kick them all off, and we're going to print out the answer in order, but that doesn't necessarily mean that that's the order in which they're done. You could actually go through that list and ask, hey, task, are you done? Are you still running? Things like this. But let's go ahead and run it one more time. Make sure I save it. Okay, we saw what it was before. Let's try again. Bam, look at that. Get him? Got him. That is awesome. I'll do it again. What you're going to see is you're going to see all the numbers, all the web requests start, and then you'll see much, much quicker all of them finish. Here, let's go. Here's the synchronous version. Remember, this is how it was before. Blah, da, 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 da. Not so amazing, right? Here, enough of that. There's a new one. Get them all? Got them all. Bam, just like that. So much, much improved. And with just a little bit of work, we had to use a async keyword in a few places and await. Most importantly, we had to switch from requests to AIO HTTP clients so that we could do all the magic is right here, really, and a little bit right there. But most of the magic is on line 19. All right. Now, one final thing that was a little bit tricky was we thought we could just make this async and it would be fine. But it turns out it was exactly the same because it was still just doing them one at a time. So we needed to start them all and then go work with the results as they were coming in. Okay. So hopefully that is a really good example. You can see the more web requests you got to make, the better. Just for fun, let's just run it one more time. Get them all. Got them all, just like that. Okay, excellent, excellent. Now, let's summarize that real quick. So hopefully to you, that feels a little bit like some sparks were some flying, some metal was being shaped, right? Things were happening. It wasn't just a fake time.sleep. Okay, so for asynchronous web requests, here's how we do it. We go and we use an async with block for AIO HTTP client session, for their gets and so on. And then we're going to await the reading of the text. Yeah. Now, if you're going to take this type of operation and apply it to your program to make your code better, you have to be able to write await and async with and things like that. You saw we couldn't just put async await on the request because request doesn't support that. So what are you going to do? Well, if you're working with an external system, a database like MongoDB or Postgres, the file system, caching, queuing service like Redis, all of these things, you can't use the regular serial synchronous libraries. You have to go hunting for ones that have async methods, that have async capabilities. So here's a few I'll just call out for you. One, we have, if we're going to work with files, literally file IO, the way that's built into Python, you say with open some file name, that doesn't work. It doesn't work with async IO, even though it's file IO. So you need to use something like AIO files, right? So this will let you read and write files asynchronously. If you're doing MongoDB, you can use something called micromongo, and this has a both synchronous and asynchronous operation. It also has a cool way to mock out your data in MongoDB, so that's pretty cool. If you're talking to Postgres, you want async PG, right? This talks to Postgres, but using awaitable operations. So you like await your queries and await your inserts and commits and so on. Similarly, for Redis, you put items and get items, very much like my producer consumer, but remotely. Same, right? You await putting items, you await getting items, and so on. All right, well, that is all I have prepared for you, but I'm happy to take questions. So just right now, before you all take off, I'll say thank you. Follow me on Twitter. Also, if you want to go deeper in this, check out my online course over, I have a 5-hour course at talkpython.fm/async that talks about a whole bunch more of this. There's one more thing, so we have a little bit of time I want to show you, but if you are interested in in-person training from Wintellect, contact Martha Guerin at mguerin@wintellect.com. And if you ask, maybe even this course could be converted to an in-person course. We'll see. Okay, now there's one. We have a few minutes left, so let me show you this real quick because this is a nice little crowning end to it. So there's this library called unsink, and I showed you this challenge before. Ooh, going back, almost there. This one, where we have this partitioning of how can you use the different threading and multiprocessing and other APIs in Python to do parallelism. If it's computational, you got to use multiprocessing or Python. If it's not async IO enabled, but does wait on external systems, often threads will make that work because say when you're talking to the network or something, the lower level bits release the GIL. So another thread could go do some work actually. Or there's the full-on async IO stuff, which you just saw. Now, if you have to do some work that's async IO and some work which is computational, how do you mix those in a unified way? That turns out to be annoying and painful and whatnot. So this library called unsink, it's literally like 125 lines in a single Python file, but it's glorious and it's API simplicity. So let me show you something here. We're going to take a couple of different operations, compute some. As you can imagine, this is CPU bound, download some more. Why are there 2 downloads? Because we're going to imagine one of these is like using a network API that has async IO capabilities. And this one is internally using a network API, but it doesn't support async IO. So there's these 2 types there. And then there's some that's just waiting, right? Just async wait type of thing. So if we run this little nosync bit, if I can get that thing to run, there you go. You can see it's, as you can imagine, it's not asynchronous. It just computes, downloads, waits. Okay. So if you try, you'll try and fail, but if you try to take this and apply the operations that you just learned with async and await, we can say, okay, what we're going to do is we're going to kick off all of these tasks, and then we're going to wait for them to be done. And we've converted the ones we can to async. So here we said async so it would actually fit into this mold, but we're not awaiting. So there's nothing happening here, right? There's no benefit. Downloading, we say async, and this one is async, but this one doesn't have the API. I just had to put this here so we could run it at once. So let's see what happens if I run this. You'll see some things like CPU bound stuff, no better. Downloading's happening really fast. Waiting happened really fast. So that some of the downloads, those didn't, but those two got sped up because they're using Async IO and so on. So these were improved. These all were crummy, okay? So you have this mixed mode. Like some of them should be done with multiprocessing, some done with threads, some done with Async IO, and that's tricky to think how to get right. So I want to show you this library called unsink. So let me just make sure we have it. Installs quick because it's only 125 lines, but check this out. Let's go over and take this code. I'm going to say run. This is not changed, right? Just like before, it's the old version. We're going to make it better. So let's use unsink here. So I'm going to say import, and let's say it this way, from unsink, import unsink. This is a good decorator that is like magic. Okay, so what we're going to do is we're going to say this whole business of creating the event loop, that kind of sucks and it's not real nice. Why can't I just call these functions and tell them to start? It's kind of annoying that I have to go to the loop and create a task and whatever. Like, could I just do this? Like, it's even annoying just to watch me type this. In fact, we'll do that, all right? Hang with me, folks. Okay, so we have these tasks, and instead of doing that, why don't we come over here and just, I'm going to say t dot results. I think it's like that for t in tasks. Okay, so we're going to say just wait until we get it done, wait until we get a response. And what we can do is we can come down here and we can say these methods. We don't have to decorate, we don't have to make them fake async. So we can say this is an @unsink operation, and this one is CPU bound equals true. So we can say unsink, this is a computational method. Do what you have to do to make that run best as it can on Python. This one is an async method legitimately. So we can just say it's unsink, right, like this. And unsink knows to run that on an async IO event loop that it manages transparently for us. This one, we didn't need this async here because it's not really async. So we'll say this is an unsync method. And because it doesn't have async, it's going to be run on a thread automatically. And again, this one is a proper one, like so. So it's going to run on the async IO event loop. But up here, when we call it, we don't have to know, oh, that's going to run in a separate process, sub-process. This is going to run on a background thread. This is going to run on async IO event loop, and so is this. It's the same API. All right, let's run it one more time and see what we get. Bam, look at that. Is that killer or what? And all I had to do was put @unsink and indicate whether it was not CPU bound or not. That's it. So instead of being 10 seconds and confusing, it's now 1 second and not confusing. Do it again. Bam. That seems to be pretty much bound up in that time. It's probably the CPU bits or something. Anyway, it's really, really nice to have this as an API to kind of bring this picture that I talked about all under one API. So I really like it. You could use it or not use it. It's up to you, but the async and await keywords do some amazing stuff, and this unsync library actually makes working with the whole spectrum of Python's async capabilities pretty slick. All right. With that, I will say thank you all, and I'll just open it up to questions. So if you have a question, type it into the little question area. Let's see. A bunch of people raise their hands. Yeah, just type it into the little question section. And while you're
Michael,
doing
do you
that,
see the questions that are in there?
I don't see them for some reason. I don't see any at all. Can you read them to me? I'm sorry about that.
I could. Hold on. Okay, so Roller is asking, will I learn a lot about async in this webinar? I'm hoping to see more practical examples that given me an idea of how I might take advantage of the async in my programs.
Super. All right. Glad it was useful, Roller. Thanks for coming.
Okay, oh, hold on, just lost him. Try it again. Okay. I've been busy with hashtag 100 days of code, so I haven't taken the async course on the Talk Python yet. Hey, Michael, a huge fan of yours show. That's what my daily commute to home, from home to the office, usually utilizes. I'm listening to you.
That's awesome.
Always
Thank you.
good.
Thank you. I much appreciate it. Happy to be on the ride with you.
Okay. Devin is asking, will be provided the slides? And that answer is yes, Devin.
Yep, they're already in that repo. I just have to do a PR to get them actually into the main one. I also just committed my code, so everything you saw me type will be there as soon as you all approve it.
Pete is asking if the code is on GitHub now.
Almost. The one that's on Mike C. Kennedy / Wintellect webinars is there now. That will be merged back to the official Wintellect webinars one today, probably.
Okay.
That includes the slides.
Okay. Could we have the sample code after the class? The answer is yes. Sacramento
Yep,
says
it's
hello.
right there. Hello, Sacramento.
And John, you missed the beginning. And what is the Python tool, he asks?
The editor, or I'm not sure what you're referring to.
All right, John, can you ask him again? He's still in the
conference.
Ask
me.
Okay.
Yeah, okay, great. Yeah, probably you ask it at a super relevant time, and I didn't see the questions because they didn't pop up for me for some reason. Okay. So anyway, yeah, ask it.
Alina is asking, how can I make my own asynchronous lib? I mean, how can I write async functions without calling await? In AIO files, they use run in executor method, but the doc says this should be used only for CPU heavy tasks. So how can I write my native sync function?
Yeah, so you can do, where did it go? Here probably is the best example. You can do this. You can say loop create task and give it that thing, and then you can inspect the task to see if it's done, and you can await it and stuff like that. Like you can see here, like task dot all tasks done, canceled, exception. So you can start it off with loop dot create task, and then you can just inspect it or just await it.
Okay.
You don't have yeah, exactly.
What version of Python should we use to start using async? 3.5, 3.7, or what?
It only exists in 3.5 and above. There were a lot of actually improvements and new features added to 3.7, I think. From 3.6 to 3.7, I think there's actually a lot of new features like this loop.create. They used to be just I think there's also an async IO.create task where it used to require you have the loop and things like that. So the newer the better, but 3.5 at a minimum.
Okay. Next is from MB. Would you start the project with the async approach or switch to it when the performance becomes an issue?
Generally, I think I'd switch to it when performance becomes an issue. There's always an overhead of doing that and dealing with it and so on. I think it's pretty easy to make that transition generally. So, the one thing you might want to consider is like certain types of things don't lend themselves to it, and it would be like really challenging to make that change. So, for example, for MongoDB, I really like to use Mongo Engine. It models the Django API for Mongo, which is really nice, but it has no async support. So if I built on that, and then I'm like, oh, I want to be able to await the database, which would be cool. It's a really good use for that. I'd have to rewrite that in MicroMongo. So if you think you might want to do that, maybe just keep an eye on to like what are the libraries you can use that are out there to make that possible, so that you don't have to completely dump some central library like a data access layer. But outside of that, I would write it normal, see how it's behaving, and then switch it over. There's a few examples where it's like completely for sure that it's going to be better, like this web scraping stuff. It's like you saw in the profiling, 97% of the time we were waiting on the internet, it's going to be much, much better like this. But often it's not that clear. So then maybe do it later.
All right. All right. Eric is asking, how do you throttle your requests so that you don't crash the server you're talking to?
So there's two types of considerations there. One is so you don't crash the server you're talking to. The other is so that you don't crash your application by getting too much back, right? Like if you're talking to the same different servers, right? I'm trying to search CNN and Fox, the New York Times and PBS. Like I'm trying to do like news discovery, right? You could, kick it off to crawl each site asynchronously and that'd be fine, right? But so you're not going to hurt them, right? But in my example, we're doing this against the same server, 15 times or 14 times altogether. So I think what you want to do is you would write a loop that would go through and keep an act of this list of running tasks here, maybe, and only start them if they get done. So you can go through and you can ask, like, if a task, you can basically go through this list and say, give me all the tasks that are done, and pull them out. But you could do one step short and put them in there and only start them. If you have the capacity. So you got to juggle it a little bit. There's in the other threading, like the executor stuff, you can do thread pools and process pools. I don't know of anything like that for these here. And you could use like a semaphore, but I feel like you kind of got to just juggle that and just don't start them all, right? Get all those in a list and then like juggle the ones that are running. I know that's not a super great answer, but there it is.
Okay, I have Alex is asking. I just lost you, Alex. Okay, is there a good webinar talk diagram that shows that what's happened behind the scenes with the event loop scheduler? More specifically, what Python is doing when you are waiting something.
Let's see if I can make this one do it here. Where's the sync? So they have the concurrency diagram for this thing. If we run that, you can see the threads that are off doing their thing, and you can see, I don't know why it doesn't. Yeah. So in theory, I don't actually know how to make it show me that. Maybe if I run the other one, I think this one. Oops, I want to do that. Do I get any? This should be showing up here, but I don't know. PyCharm's supposed to have something that shows me that, right? Like this async IO graph should be showing me that. Maybe it has to be at a breakpoint. I'm not really sure.
Are you ready for the next question, Michael?
Yep, hit me.
Okay. All the great async things are available in Python 3. Is it possible to achieve something similar in Python 2, legacy Python, any external libraries?
It's possible. I mean, there's things like gevent and Greenlit threads. There's some things like that. Some of those libraries, like Twisted, for example, you can do some things like this. It's just not as general purpose.
Okay, and the second part of that is, if you were to write async web app, would you use AIO HTTP directly or some other library, and why?
I would definitely use some other library. So there's a couple of libraries. If you're doing Flask, you can use something called Court, and that will let you make your view methods that do the web processing asynchronous, and it's basically the same API. If you're doing Flask, spelling is hard, Flask APIs, I would look at Sanic. That's a really good one as well. I think if you're doing Django, there's Django channels, but I don't know how general purpose that is. I'm not sure it's 100% there. Django itself is supposed to have async capabilities, but it's like a couple years out. It's quite far out. So there's also API star, I believe, is an option here.
Okay, ready?
I'm ready.
How do you control limit the speed that you send requests when web scraping?
Yeah, I mean, that's kind of the same bad answer I gave before. It's like here we're just saying start all of them. What you might do is, so maybe this is an answer for the folks. So you could, import iter-tools, then what is the right? I know there's something here for this, but I'm gonna just make something simpler. So what I would do is I would say, okay, we're gonna get all these items. So maybe something like this will give them to you on task source, and then something like come down here and you say next 10 or however many you want to do equals task source. Give me the 10, right? And maybe off by 1, right? And then go and do all this. Here, let's just do. There. So something like this would say, okay, I'm going to go after all of these URLs, right? There's only 15, but you could imagine it's like 10,000, right? And then we're just going to loop around and say, get me the next 10, and sort of drop from the list. So now you got 5 left or whatever, and then kick off of those 10, process them, go back in, get the next 10, process them, go through. That's kind of what I was stammering about before.
Okay, and I hope I can say this correct, because you need to actually see this, I think. What is the difference between loop create task and async IO ensure future, and when do you use each?
Create task versus ensure future. I believe they're quite similar, but I honestly have to look into it more. I don't know.
Okay. Unsink looks awesome. Links,
yeah,
please, which
awesome.
We've already covered that. Thanks, Michael. Great to finally meet you. Yeah. Python 3.7 has this new trio style Async IO run. Are you aware of that? What that's all about?
Sorry, could you read that last question again? I was just pulling up the link for unsync for folks.
It says Python 3.7 has this new trio style Async IO run. Are you aware of what that's all about?
Yes, I believe so. So let's go here. So over here we could say async IO.run, and we could give it final task, I believe. And I think what this saves us from going and creating the loop and then saying loop.run to completion. I think it just does those two all at once. Yeah, it takes care of managing that bit right here. So yeah, so it's already running, that's a problem, right? So it'll get a new event loop and then set it and then run till complete. Yeah, so pretty much. I mean, it's slightly more complicated, but it like combines that step with that step, those two steps into one.
Oh my gosh, there's still a lot of questions coming in. Let us know at what point you need to go away, and we can do this through our question and answer through email.
It's okay. It's
Easier.
all right. Keep them coming.
Okay.
I got a little time.
Okay. Can I use unsync even if I only want CPU power?
Yes. Yeah. You don't have to use all of it. It lets you work in a unified API against the 3 different types: CPU based, threaded based, and async IO based. But you could just turn it loose on any one of them, and it generally makes them better.
Okay. What is the biggest difference between async in .NET and Python?
The things like async and await are super similar, right? This IO, breaking stuff up into little slices and doing the work on this like visualized async event loop on the same thread. That's all very, very similar. The biggest difference really is the CPU bound stuff does not work on threads. .NET and Python all have thread pools. We didn't talk about that here, but Python has a thread pool as well. The main difference is threads will not do anything computational for you. So you have to do that through multiprocessing, which means like there's a slightly different API, and that's kind of annoying. I showed you unsync to like get around that. But that if there's one big difference, it's the Python GIL and the fact that it doesn't matter if you have 100 threads, you can only do one Python thing at a time. Those can talk down into the C layer of, say, like NumPy or something, and then those can go in parallel. There's other options, but the quick 30-second answer, that's it.
Okay. How do you handle Py 3.5 code mixed with async aware if you want to write a lib?
So I think probably the best thing that you could do is make sure that you run your tests and your continuous integration under Python 3.5 and not just the newer ones, because like I said, there's certain things like async IO, loop create task versus async IO create task. Like I think the async IO create task came in a later version of Python, so like you could easily use a piece that's not in the older versions of Python. So if you use something like Tox and you make sure your tests run on the latest version and the oldest, sort of in quotes, oldest 3.5 version of Python that supports this at all, that seems like the best option.
I lost where I am, so I'll grab something from the bottom until I find my way back. Why didn't you do async IO gather tasks for the list of tasks in the web scraping example?
On here? Let's see. This is the web scraping one. I think I did. Maybe there's something I'm missing about, but that's async gather tasks. Async IO.gather tasks. Maybe instead of combining these together, I'm not sure.
Okay. What is the difference between main thread and background thread?
Okay, main thread is the thread of execution that runs when you just start your program. It starts with one thread and it just starts going top to bottom. Background threads are other threads. Let's start with that. Are threads that either you or a library you call create, right? So for example, over in this unsync thing, when I called this, not that, called those, there are 2 other threads created managed by unsync, but I could have explicitly done that. Those are background threads, sort of. Background threads technically are also ones that are set to be in what's called daemon mode, which means it won't keep the process alive if the main thread exits. But I kind of mix those together in my mind, just talk about main thread and other threads. Stuff that didn't start because your program's running, but started because your program chose to do other parallelism things explicitly.
Okay. Could you please talk a little about async and multiprocessing work together? I think that means how they work together.
Yeah, they're just sort of 2 independent things, right? Like with multiprocessing, you're taking some of the work, you're snapshotting the memory and moving it over to a background process that's running that function in Python over there. You can also be doing async IO multiprocessing while that's happening, and then come back and then say get the result from that other process. yeah, they just basically mix together well. Like you saw that here, actually, all of this was happening on Async IO, and all of this is happening on multiprocessing. And they just both go do their things, and you can come back and ask for the answers. Right here, it's a little easier because unsync unifies that, but you could say, give me all the Async IO answers, give me all the multiprocessing answers, and carry on. You can also do multiprocessing in the back. You could do Async IO in the other process, right? Like you can sort of have this chain of them, but you probably shouldn't too much.
What are your favorite synchronization techniques for interlocking data structure access in your first example?
Yeah, so maybe in this one here, maybe you would do something to the effect of, let's see, import. Generally rlock. In the threading library, there's a lock, and there's an rlock. The lock is generally bad because it more easily deadlocks your program. Rlock, the R stands for re-entrant lock, and that's a little bit less error prone. So start there. And you can use other things as well, but that's the starting point.
Okay. Are there any libraries or apps that help with async conversions?
With async conversions, oh boy. Well, there are libraries like the AIO HTTP that allow you to like swap out synchronous bits for asynchronous bits, or async PG, things like that. But I don't know of anything that's like going to convert it for you, really. I would say what you should do in terms of helping is like what you saw me do with this web scraper one, this one. When I ran this in the profiler and I said, oh, it's spending 97% of its time here. How do I make that async? And it turns out like that was enough just to fix that one part, right? So measure it with a profiler, and then find the worst spot and ask yourself, can we make that part async with some other library?
Okay. Do you prefer VS Code Sublime do you prefer VS Code Sublime for PyCharm?
I definitely prefer PyCharm over VS Code, and very much over Sublime. But VS Code is coming along. It's a nice editor. I use it some of the time. I have it hanging out right here. But my vote's still for PyCharm. It still is a little more cohesive, and that's a little more tooling, like that, right click, show me the profiling results. That kind of stuff's really nice.
Okay. This one says, hi, I use SQL Alchemy as ORM, but I couldn't find any async option able to fully replace it. What would you suggest? Thanks.
Yeah, I know. It's tough. I don't know what a real great answer is for that, because I talked to Mike Bayer, who was the creator of SQL Alchemy a while ago, actually, a couple of years, and he said, we looked at it, we don't think there's really any benefit to using async here. I disagree a lot. Disagree a lot in terms of, if you have a slow database, you can do a lot more, but he may have changed his mind since then. Last time I spoke to him, he said, we looked at it, we don't really think this makes any benefit to add it to SQL Alchemy. You probably could search for some stuff, SQL Alchemy, Async IO, but there's some add-ons, but I don't know of anything. Like here, this is the article he's talking about that we spoke about. But maybe this. It's not an Async IO operation, yeah. Yeah, I don't know. Anyway, maybe this thing helps. I'm not sure. I have no experience with what this thing is. But these are the types of things you got to start looking at.
Okay, this one says, hey, Michael, thank you for the webinar. We are using Async IO in our code. Are there any tips to make it even better? Unsync seems cool. I want to try that. Is there anything else that I can try out?
A couple of things, I guess, are pretty good. There's Trio. Trio's pretty good. Apparently it's on my site. Trio is a nice library, and then there's Curio from David Beasley. Those two things are kind of similar. Those are good sort of foundational libraries that are worth checking out. And also all the web frameworks I talked about, right? Wherever they were, somewhere there. Right, Court, Sanic, API Star, Django Channels with a S.
Are you ready?
Let's do it.
Okay. Said, on your timeline slide illustrating the effect of async await, chunking up the overall runtime of operations, the total time devoted to any operation, red, yellow, etc., is not actually shortened. It's simply distributed. If the effect of async await in the case is not faster code, what would the point be?
In that case, there's no point. But let me go back to a different graphic I drew for you. In this case, so I would have colored that little thing purple in my visualization. Framework, RCode framework. Those are the four things that would appear here. But what's not even in the list is waiting on the database the first time and waiting on the database the second time. So because maybe from here to here is waiting on the database, and then from here to here is waiting on the database. So you're letting other work happen during those holes in execution. So it is much faster, right? Like if you go back here, it's like basically Async IO lets you, in some sense, take away the green. Hopefully that makes sense.
Okay, I'm trying to understand what this one says. What does the air quotes with statement did alongside with async keyword? I didn't understand it.
Yeah, it's a little bizarre the first time you see it. Let me find an example. I'll show you. That would be here. So this is probably not exactly right, but it's something like this, like session equals AIO HTTP.client session. Wait, await, and then with session ... right? That bit right there is the same as that. Basically, it's not exactly the same, but it's like you see, it's giving me an error. Like you can't do that because but it's like I'm going to, in one statement, call this operation and await getting it, and then I'm going to put it into a context manager that will let me clean it up successfully. But instead of making you jump through hoops to try to do that, there's a one-liner way here. Hopefully that makes sense. It's definitely a bizarre syntax, but it's handy.
Okay. Any better practices to handle exceptions?
Handling exceptions, yeah, that can be tricky. The async and await make handling exceptions a lot easier. I didn't really talk about that, but when you kick off a thread and there's an error, it can get lost and it's in an error state, and then all sorts of bad stuff happens. With these, if you here, if you put that into a try except clause and there's an error, that it'll be thrown correctly. Also, unsink does a lot of stuff to make exception handling nicer, and for all those, it'll bring the exception back over.
Okay. Are there async capable libraries for calling out to the terminal or shell on the various OSs? For example, calling out to PowerShell scripts doing Active Directory stuff on a Windows server.
I don't know. It sounds almost like you're talking about subprocess and starting subprocesses. Yeah, it sounds like, I would say maybe see if some unsync magic will help you there. It sounds almost like you need to actually run those in threads, but let me look real quick. Maybe. Oh, here we go. How about that? So we have an async IO create subprocess, and then that one you can await. right here. So if this is a PowerShell script you're trying to run, you're going to start it as a subprocess. You can await it here. I think that might be what you're asking for.
Okay, how about using async and Django without using Django channels? Is there a benefit for it for a classic website?
For the most part, I don't think you can use Async IO with Django without some add-on or some sort of change to it. Right now, like the web methods can't be async methods and so on. What you could benefit from is like if you call a function in Django and that thing wants to go call 3 services in the database, you could create an event loop there, go do those 3 things in parallel, gather up the answer and give it back. But I don't think you can actually make the Django requests themselves async like you can with Court or Sanic yet. They're talking about it. There's the Django async roadmap. Have a read on this.
Okay, and any tips for debugging when using Async IO?
Not a bunch of huge tips. There's this little thing down here, this concurrency diagram that's supposed to do a thing. I've never been able to make it work, but if you research it, maybe you can. What you saw me do on all of these actually was to use color, right? So you can use Colorama to like have it clear what part's doing what and how it's interlacing the different behaviors. I just find printing in Colorama lets you conceptualize that a little better. It's not a huge help, but a little bit.
Okay, last question. Any suggestions for unit testing in async world?
I think there's a plugin for PyTest, I'm pretty sure. I can't remember what it's called. Well, very mysteriously named PyTest Async IO, as you can imagine. So it lets support, it basically handles the event loops and stuff for you, right? So down here, you can mark your test as an async IO test, and you then can have async methods that await things, and there you go. So
okay.
PyTest-async IO.
I think we're good.
All right. Well, I see there's 84 of you still left, so thank you all for sticking around and listening to all the questions and coming today. And thanks, Kim and Martha and Wintelect for having me here.
Thanks, Michael.
Yep, bye.